So consider these two sets of simultaneous equations here, where the demand function is given by the output of Q, um, P being the determinant, and it also has an exogenous X variable, where the supply function just has a Q equals P. Now in this case, the Q and P variables are considered endogenous variables because their values are determined within the system. Whereas X, we can say it's income or whatever. Well, not whatever, because if we say it's income, it will be determined outside of the system or it is independent. Now, just from the first lesson, that might be a little confusing on how we can determine which variables are exogenous and endogenous. The easiest way to kind of interpret that is if the variables are kind of already determined, if we can't control any part of the variable, like our quantity and price are kind of already predetermined, while our x variable we can kind of manipulate. I'd say that's the easiest way to distinguish exogenous and endogenous variables. In like a problem or theory problem set, you're most likely going to be just like given which are the exogenous and endogenous, but in the real world, they are hard to distinguish, and that's the reason why the problem of endogeneity exists, or why it's so concurrent. All right. So since Q and P are endogenous variables, we have to rewrite these set of functions in a form of exogenous variables because we don't want endogeneity in our regression function. And so the way we do that is we'll algebraically, we'll set demand equals to supply, Q equals Q with this part of the function equaling to this. We'll make it into a reduced form model using algebra. We'll have an algebraic form of P written here, and then we'll input the Q function into the P here or here. This being the result. All right. And so in order for this process to be possible, we need to meet the requirements of what we call identification. And so if m is the amount of endogenous variables in a set of simultaneous equations, right here we have 2, so m would equals 2. Then we need m minus 1, so one exogenous variable, to be emitted from each equation. So L, we often write L as short for an instrumental variable or exogenous variable, while B will be the endogenous total endogenous variables, while L will be the IV or exogenous variables emitted. So I should probably write that. So considering these kind of definitions of L and B into factor, if L equals B, then that's what we'll call the exact identification. If L is greater than B, aka if we have more exogenous variables emitted than the total amount of endogenous variables present, that's what we call the over-identification, and if it's less, then it's under-identified. So given our first example here, our same set of functions of demand and supply, we have one total exogenous variable and two endogenous variables. So we have two endogenous variables, and so we need to omit one exogenous variable from each equation. We have one exogenous variable, a total of one exogenous variable, and so that because that belongs in the demand function, we technically don't have any omitted exogenous variables in our demand function because that is our only exogenous variable here. So we conclude that the demand function does not have any omitted exogenous variables because this is our only exogenous variables and it's part of the demand function, while the supply, we can kind of see that this is omitted from the supply function. So for the supply function, we have one omitted variable for exogenous, for the exogenous variable. And so because we have no omitted else for the demand, we can see that's under-identified. So amount of omitted is less than the total endogenous. Is this? Hold up. You should, okay, I think this is -1 because so total endogenous variables -1 because we need n-1 exogenous variables. So we have no omitted for the demand, so it's under-identified. And then for supply, we have exactly one identified, which is what we need. We need one exogenous variable to be omitted from each equation, and that's what the supply does. So it's exactly identified. All right, looking at another example, a little harder one. These y variables are just given by y, x, and z variables are just given by just some kind of given symbolically. So x and y are endogenous and z are exogenous in this case. Looking at the first function, or okay, before we do that, we should always count how many endogenous variables we have because we need to determine how many exogenous variables we need to omit. So y, which is 1, x1, and x2. So 3 endogenous variables present, and so we need to omit 2 from each equation. And so the first equation, we have only z1 as our endogenous, exogenous variable, not endogenous, exogenous. And we have omitted z2 and z3 because that is part of our simultaneous equations. So because we have omitted z2 and z3, we have exactly the amount of omitted variables necessary for identification. In contrast to the second regression, the second equation where we only have z1 omitted, even though we need to omit two exogenous variables for the equation to be identified. So y2 is under-identified, y1 is exactly under-identified, and y3 has no instrumental variables. They're all omitted, z1, z2, and z3, so it's over-identified, given here. And so recall that we need at least n-1 exogenous variables for the identification to work. And if identification works, then our reduced form model for putting our equation into kind of this form where we put the variable or function into exogenous variables only, we can actually do that if it's exactly or over-identified. And so y and y3 pass the test of being able to be reduced into exogenous variables to avoid endogeneity after being put in that form. But y2 does not because it does not have enough omitted variables. And finally, if you recall the Sargon test, what the Sargon test does is it'll look for the surplus moment condition of validity. So in other words, it needs the amount of kind of over here, it kind of needs the amount of instrumental variables omitted for the Sargon test to work. And if it doesn't work, if we do it on the software and it doesn't work, algebraically, if we try it, then we'll just get like no solution or not enough information to complete the solution. Not necessarily no solution. We just don't have enough equations to solve for the reduced form. By software, it will just return an NA because it doesn't have enough information. Yeah. There is a lot more algebra to simultaneous equations than what I introduced here. I didn't really go through any algebraic problems, but again, when I'm going through these, I want to make it more conceptual. So that's what I kind of aim for in this video. All right, so that is basically it for endogeneity. I'll apply problems of endogeneity in the next few videos, but in the next video, I'm going to go over the pooled and the panel data, which includes like heterogeneity over time. So kind of heteroscedasticity and autocorrelation kind of combined into one. Not exactly what I just said, but pretty similar to it.